Okay, so I'm going to start now. And today we're going to finish up section 14.1 of Dummit and Foote, which is the basic definitions of Galois theory. Right. So last time we were in the middle of this proof. We were trying to prove proposition 5. But let me recap and say what this is about. Right. So we have this question. How many automorphisms are there of a splitting field? And again, we're interested in this question because a splitting field should have the maximum number of automorphisms possible, because whenever you have an automorphism, it has to take an algebraic element alpha to beta, and both of these have to be roots of the same minimal polynomial. So any automorphism has to permute the roots of polynomials. So splitting fields include all of the roots of a certain polynomial. So we expect them to have as many automorphisms as the maximum number allows. So proposition 5 says this maximal number is the degree of the extension. So I'll read the statement. Let E be the splitting field over F of the polynomial f of x with coefficients in the ground field F. Then the order of the automorphism group, i.e. the number of automorphisms there are, is bounded above by the degree of the extension, and it's actually equal when f of x is separable. And this is a mild condition. It's not really that notable because most of the polynomials we know about are separable, at least the irreducible polynomials. So yeah. So any splitting field has this number of extensions equal to the degree of the extension. So how do we prove this? Well, we're going to work in a little bit more general setting where instead of looking at automorphisms, we're looking at isomorphic fields. Where instead of extending the identity element of F, so this is the identity automorphism of F, we're going to give a specific isomorphism between F and another field and extend this. So instead of extending the identity on F, we're going to extend an isomorphism of F. So theorem 13.27 says if you have an isomorphism between fields, then it can be extended to an isomorphism between splitting fields. Okay, I just need to erase this. All right, so we already know this theorem. Right. Given an isomorphism between f and f prime, phi, there exists an isomorphism between the splitting fields of f and the splitting field of f prime, sigma. F prime is the image of f under the isomorphism between the polynomial ring with coefficients in f and the polynomial ring with coefficients in f prime induced by the isomorphism phi. What we want to prove is that the number of extensions sigma, the number of possible extensions sigma between the splitting fields, this isomorphism, this is bounded above by the degree of this extension. And the number of extensions is actually equal when f of x is separable over f. Okay, so it's kind of weird. We're relating the number of extensions of an isomorphism to the degree of the extension. But this proof, if you understand it, you'll understand why it works like that. I'll tell you in a bit. So the idea of this proof is to induct on the degree n, which is the degree of the extension E over F. So we're going to assume this statement holds, i.e. there are the degree number of extensions when the degree is less than a specific number, and then try to prove it for that specific number. So first, let's do the base case. The degree of the extension is equal to 1. So suppose the degree of the extension E over F is equal to 1. Then E and F are the same field, so there is a unique extension of the isomorphism phi to sigma, and it's equal to phi. So the base case is easy. Degree 1 extensions have unique extensions of isomorphisms. Now the induction step. So in this induction step, we're thinking about the case where the degree is equal to n, which is greater than 1. We already considered the case n equals 1. So assume n is greater than 1, and also assume that the result holds for all extensions of degree less than n. So this statement is the induction hypothesis. And again, what do we mean by the result? Is this thing that we want to prove. The number of extensions is less than the degree. So if the degree is less than n, the specific n, we're saying that the number of extensions sigma to E would be less than that number that's less than n. And if it's separable, if it's a splitting field of a separable polynomial, this number of extensions would be equal. Okay, so now this is our induction hypothesis. How do we do the proof? So the idea is to count the number. So we're trying to count the number of extensions sigma. And the idea is that this is equivalent to counting the number of diagrams that look like this. So before I can say why it's equivalent to this, let me explain what these diagrams are. Right. So first of all, before I can even, specifying a sigma gives us, okay, no, let me just explain the diagram first. So first of all, the case we're in is the case where n is greater than 1. So the extension E over F has degree n, which is greater than 1. So in this case, there is an irreducible factor of the polynomial that we're taking the splitting field of, which has degree greater than 1. So call this factor, this irreducible factor of f, call it p of x. And then fix alpha to be a root of p of x. Right. So we're doing all of this before we even choose an extension sigma. Right. So forget about sigma. Just think about fixing alpha as a root of p of x, which always exists because the degree of the extension is greater than 1. Now we're still not even talking about sigma yet. So the isomorphism phi from between the ground fields f and f prime induces an isomorphism between the polynomial rings with coefficients in f and the polynomial ring with coefficients in f prime. And this isomorphism between polynomial rings carries f to f prime. So this polynomial to this polynomial, it also carries this irreducible factor of f to this irreducible factor of f prime. And we're going to call the image of p of x to be p prime of x. Right. Okay. Any extension sigma from E that so now at this step we're going to care about sigma, which is the extension, which is an extension of phi to the isomorphism between splitting fields. So any extension sigma restricted to f of alpha, so alpha is this fixed root of p of x, is an isomorphism onto its image, which is some subfield of E. So what am I saying here? You have, we fixed this alpha before we chose sigma, and now we look at a specific sigma, and then we say that it takes this subfield f adjoint alpha of E to some subfield of E prime. So this should be E prime. Right. Right. So we get when we restrict sigma to F adjoint alpha, we get an isomorphism onto some subfield of E prime. Hold on. So there. Okay. So that's so now I still have to say what is tau and so on. So I'll say it in this statement. So each choice of sigma, right? Each sigma determines a unique diagram that looks like this. So sigma is already an extension of phi, but it determines a unique diagram that looks like this. So what is beta? Beta is the image of alpha. And what is tau? Tau is sigma restricted to F adjoint alpha. And notice that tau is completely determined by its action on alpha, and beta is some root of p prime of x. Right. So now we know what these diagrams are, and we're saying if you give me an extension sigma, then I can draw this diagram that determines this unique diagram. So yeah. So what information is given in a diagram? Well, alpha is fixed before, so alpha is always fixed. So this is not any unique information particular to a diagram, but beta can be chosen to be any root of p prime of x, right? And then choosing beta determines tau, right? Tau is completely determined by its action on alpha. Tau is sigma restricted to F adjoint alpha. And we know how F gets mapped to F prime. We just need to choose an image of alpha. And if we choose beta, then we essentially determine tau. And then sigma can be chosen to be any isomorphism restricting to tau. And the point is some choice of sigma always exists. By theorem 13.27. Right. So for any diagram, there exists a sigma which gives it. Right. So there are two statements here. One is that fixing a sigma, we determine a unique diagram, and fixing a diagram, we know there exists a sigma that determines it. Right. So does that make sense? Right. So our idea originally was that counting the number of extensions is equivalent to counting the number of diagrams that look like this. But what is the information specified by a diagram? It's this map tau and this map sigma, right? And the point is, for any choice of beta, there exists a sigma and a tau that give us this diagram. So yeah. Okay. So now the question is, how many extensions of phi are there to a certain tau? So tau is this extension of phi to F adjoint alpha onto F prime adjoint beta. So beta can still be a choice, but alpha is always fixed, right? So how many choices do you have for extending phi to a tau? Well, like I said, this is given, tau is determined by beta. So it's equal to the number of choices for beta. And then this is less than or equal to the degree of p prime of x. Why is that? Because each beta is a root of p prime of x. And how many roots do you have of p prime of x? Well, you have less than or equal to the degree of p prime of x. right? If you had more roots than the degree of p prime of x, then p prime of x would actually have degree greater than what it actually has, because then you could write it as a product of monomials, and then the degree would be greater. So the number of roots is less than the degree of p prime of x, but when p of x is separable, this is equal, right? So the degree of p prime of x is equal to the degree of p of x, which is the degree of the extension f adjoint alpha over f. Because p and p prime of x are both irreducible, so they're the degree of the extension that you get by adjoining a root of the polynomial. Okay, so now we know how many extensions of phi there are to tau. It's less than or equal to the degree of the simple extension, and it's equal when the irreducible factor is separable. Okay, so now let's finish off the proof. So how are we applying the induction hypothesis? So we're using this thing. Since E is also a splitting field of f of x over f adjoint alpha, right? E is a splitting field of f of x over f, but f of alpha contains f. So this polynomial also has coefficients in f adjoint alpha. So and E has all of the roots of this guy. So it has all of the roots of this guy over this coefficient field as well. So since E is a splitting field of f of x over f adjoint alpha, and E prime is also the splitting field of f prime of x over f prime of beta, and the degree of the splitting field over the base field, now we're considering f adjoint alpha as the base field, is less than n, right? So this inequality is true because it's a smaller extension, and this is n, we can apply the induction hypothesis. And the induction hypothesis tells us that the number of extensions of tau, now we're fixing a tau between the new base fields f adjoint alpha and f prime adjoint beta. So tau is an isomorphism between these two guys. The number of extensions of tau to sigma between the splitting fields E and E prime is less than or equal to the degree of the extension from the base field to the splitting field. So the degree of E over F adjoint alpha. So the number of extensions of tau to sigma is less than or equal to the degree of E over F adjoint alpha. And it's also equal when the polynomial f of x is separable. From the degree of E over F being equal to the degree of E over F adjoint alpha times the degree of F adjoint alpha over F, the number of extensions of phi to sigma is less than or equal to this total thing. With equality if P of x and F of x are separable, i.e. if F of x is separable. So let me just say this a little bit more slowly and again. So we have phi and we want to extend it to sigma. We know how many ways there are to extend phi to tau, and then given the specific tau, we know how many ways there are to extend tau to sigma. So the number of ways to extend phi to sigma is the number of ways to extend phi to tau and then tau to sigma. Phi to tau is this number, and phi tau to sigma is this number. So the number of extensions from phi to sigma is their product. Yes. So you have to pick a choice for this extension. This extension. F adjoint alpha over F is the number of choices from phi to tau. And then E over F adjoint alpha is the number of extensions from tau to sigma. So the number of extensions from phi to sigma is F adjoint alpha over F times E over F adjoint alpha, because the number of total choices is the number of choices here times the number of choices here. And that product is E over F, the degree of E over F. And again, equality if you had equality here and equality here. But to get equality here, you needed P of X to be separable, and to get equality here, you needed F of X to be separable. So you have equality here when P of X and F of X are separable, but the condition that P of X is separable is included into the condition that F of X is separable because P of X is an irreducible factor of F of X. So we just needed F of X to be separable for this to be equality. So in conclusion, the number of automorphisms of a splitting field over F is less than or equal to the degree of the splitting field over F, with equality when the polynomial you're splitting is separable. Okay. Are there any questions about this argument? I'll make a note. Why did we have to go through the trouble of starting with F and F prime? Why couldn't we just extend the identity on F? That's because when we do our induction hypothesis, we're going from adjoining some root of alpha to some root of beta, some root of f of x to some root of f prime of x. In the case where f equals f prime, and this is the identity, we're going to look at extensions between f adjoin alpha and f adjoin beta, where beta may be another root of the same polynomial, but they're still going to be distinct fields, right? And then when we try to use the induction hypothesis, we really needed, over here, when we tried to use the induction hypothesis, we really needed to extend isomorphisms between two distinct ground fields, f adjoin alpha and f adjoin beta, right? Alpha and beta are going to be distinct roots, and you have an isomorphism between them, but it's not the identity isomorphism from f adjoin alpha to f adjoin alpha. So in order to use the induction hypothesis, we really needed to start with a more general setup. And this is something I find cool about induction arguments. Like, okay, so this is a side note from the proof. We finished the proof. But something cool about induction is that when you try to prove a statement about induction, it's sometimes easier to prove a more general statement, because when you try to apply induction, you can apply a more general induction hypothesis, right? So if you start with a more general statement, then your induction hypothesis is more powerful and gives you more flexibility to use in your argument. So that's why we started with a more general statement, because in the induction hypothesis, when we try to use the induction hypothesis, we required it. Okay. So yeah, that's proposition 5, and that's basically the last main theorem in this section. It's about the number of automorphisms of a splitting field, and it's related to the degree of the extension. Okay, any questions? Okay. Now, what did I write here? So the number of automorphisms of E over F is equal to the degree of the extension, in the case E is a splitting field of a separable polynomial with coefficients in F. Exactly. In general, we can modify the proof that was given above there to work with any finite extension K over F, not just splitting fields. But in those cases, we're going to get an equality. We cannot claim that the automorphism group of a finite extension is equal to the degree, because sometimes you won't have enough automorphisms for it to be equal to the degree. But in the case of a splitting field, it is equality. And in general, when you have a finite extension, you have an inequality, right? Less than or equal to. If it's a finite extension and it's not a splitting field, it's usually less than. And we'll prove this later. Okay, so the question now is, when do we have enough automorphisms? So when do we have that the order of the automorphism group, the number of automorphisms of this extension, is equal to the degree of the extension. And we have a name for these kinds of extensions, and they're called Galois extensions. So examples of this are Q will join the square root of 2 over Q. We have two automorphisms, the identity and the automorphism that takes square root of 2 to minus square root of 2. And notice that 2 is also the degree of this extension. It's a quadratic extension, so it has degree 2. And furthermore, this is a splitting field, right? It's the splitting field of the polynomial x squared minus 2. So we know it's a Galois extension just by the previous statement. Okay. Next, this is a non-example. Q will join cube root of 2. Well, how many automorphisms of this extension do you have? You only have one automorphism, which is the identity automorphism. If you think about it, any other automorphism has to send this generator's cube root of 2 to another root of the minimal polynomial x cubed, x squared, or no, x cubed minus 2, right? But what are the other roots of this guy? You have one real root, and then you have two complex roots. They're conjugate. Omega times cube root of 2, omega squared times cube root of 2. But none of these things are contained inside of this field, which you're trying to take the automorphisms of. So you have nowhere to send cube root of 2 towards. None of the other roots are in this field. So that's what goes wrong when you don't have a splitting field like we were assuming in the previous theorem. You have nowhere to send cube root of 2 to other than itself. So the only automorphisms of this extension are the identity automorphism. However, this extension has degree 3 because it's a cubic extension. You're adjoining a root of the polynomial x cubed minus 2. This is irreducible, so the degree of this extension is the degree of the polynomial, which is 3. So the order of the automorphism group is 1, but the degree of extension is 3, and this is a strict less than. So later on, we're going to see that Galois extensions are basically splitting fields. If you have a Galois extension, you can write it as a splitting field of some separable polynomial, but we're going to prove this later on. So basically, Galois extensions are just splitting fields, but the fact that splitting fields are Galois was that whole argument up there by induction, and now you have a better understanding why that's true. And the fact that Galois extensions are splitting fields, we're going to reserve this till later. So we're also going to reserve the proof that the automorphism group has degree less than the extension for later as well, using a different type of proof. Okay. So a finite extension K over F is Galois if the degree of the automorphism group is equal to the degree of the extension, i.e. you have the maximum number of automorphisms. In this case, we use the notation Galois K over F. GAL of the extension is to denote the automorphism group. So only in the case where you have the maximum number of automorphisms do we write Galois, right? So you can't write Galois of this extension because this is not a Galois extension. Okay. And this is what I was just saying. We will see the converse is also true, which completely characterizes. I forgot to say. So if K is a splitting field of a separable polynomial over F, then K over F is a Galois extension. That was the thing that we proved by induction up there. The splitting fields are Galois extensions. We will see the converse is also true, which will completely characterize Galois extensions. So later on, we're going to prove that any Galois extension is the splitting field of some separable polynomial. So this completely characterizes Galois extensions, meaning that Galois extensions are just splitting fields, and splitting fields are just Galois extensions. But we're going to prove the force this direction later. Okay. Now, definition: f of x if f of x is a separable polynomial over f, then the Galois group of f of x over f is the Galois group of the splitting field of f of x over f. Reasonable definition. So the Galois group of a polynomial is the Galois group of the splitting field of that polynomial. And now the rest of this chapter is a bunch of examples. There are like eight examples, I think. I don't know. And I'm just going to speak about examples for the rest of this lecture. If you have anything in particular you want to ask or anything you want to look at, then we can look at that together as well. Just tell me what you want. So first example, q adjoins square root of 2 over q. This is a Galois extension. It is the splitting field of x squared minus 2. Okay, what are the automorphisms? Well, aside from the identity, you have to send square root of 2 to minus square root of 2 because that's the only other root, only other option you have. So those are the two automorphisms in here. So the Galois group is Z2 or Z mod 2Z. Because if you apply the automorphism twice, then you get the identity. Square root of 2 to minus square root of 2 to square root of 2, which is the identity. So remember last time what I said, the goal of Galois theory is to relate the group of permutations of the roots of a polynomial to the algebraic structure of the splitting field. And you can see how we're doing that. We talk about automorphisms of extensions, but really all we need to do is specify the action on some generators, which are usually roots of certain polynomials. So really we're just, whenever you have a Galois group, you're really just permuting roots of a certain polynomial. So that's what Galois theory is about. Okay. Now, more generally, if K is a quadratic extension of F and the characteristic of F is not equal to 2, then you have a Galois extension. A quadratic extension means you're adjoining a square root of D, some number. And you have two automorphisms. Square root of D gets sent to minus square root of D, and just square root of D gets sent to square root of D. So the identity and the conjugation operator. Is there anything else to say here? Quadratic extension is equivalent. So, okay, not Q adjoins square root of D. What I meant was F adjoins square root of D. So we're taking a quadratic extension of F. Technically what quadratic extension means is a degree 2 extension. But whenever you have a degree 2 extension, K over F, then you can prove that as long as the characteristic is not equal to 2, that extension is of the form square F adjoins square root of D. So try to prove this. It's pretty easy. Like when you have a degree, so what I'm saying, you have degree 2 implies K is F adjoins square root of D for something, as long as the characteristic is not equal to 2. Yeah, okay. Now, cubic extensions, this is not a Galois extension, like I keep saying. Q adjoin cube root of 2 is not Galois because you only have the identity automorphism, which is not the degree of this extension. The splitting field of x cubed minus 2 is actually q adjoin cube root of 2 adjoin omega. And in this case, this is a Galois extension because you can send cube root of 2 to 3 different possibilities. The other roots, cube root of 2, omega cube root of 2, and omega squared cube root of 2. So you have 3 distinct possibilities. So the group of that splitting field would be Z mod 3Z. And yeah, the generator would be the one that sends cube root of 2 to omega cube root of 2. Because if you do this twice, then you're going to send this to omega squared cube root of 2. The generator also sends omega to omega. But without having omega, this is not a Galois extension. Now, biquadratic extensions, meaning I guess just extending two quadratic elements. That's usually what I think biquadratic means. You're okay. So are all Galois groups symmetric groups? No. Let's look at this example. This is a good example. So I'm claiming that this is a Galois group. This is a Galois extension. Q adjoins square root of 2 adjoin cube root of 2. Why? Because this is the splitting field of this polynomial, right? You have all of the roots of this polynomial. Square root of 2 and square root of 3, minus square root of 2 and minus square root of 3 are all roots of this polynomial. And this is a degree 4 extension, which is the degree of this polynomial, right? So, wait, is that what I wanted to say? I mean, if you adjoin, no, that last sentence I said is not the correct logic. If you adjoin all of the roots of this polynomial to Q, then you get Q adjoins square root of 2 and Q adjoin cube root of 2. So not only does it have all of the roots, it is the smallest field generated by all of the roots. So therefore, it's a splitting field. So we know it's a splitting field of a polynomial, and over Q, all irreducible polynomials are, well, this is not irreducible, but it's a product of irreducible polynomials. So each factor is irreducible. So each factor is separable, and then therefore, also none of them have overlapping roots. So yeah, this has 4 distinct roots, and that's equal to the degree of the polynomial. So it's a separable polynomial, and yeah. Oh, because not all roots can be permuted with any other root. Exactly. Yes. So what are the automorphisms of this extension? Well, there's the identity, first of all. There's the automorphism. Any automorphism. Okay, I should write this down. Let me write this down. So let's say you have some automorphism sigma. Sigma is an automorphism of Q adjoins square root of 2, Q adjoin cube root of 2. Okay, come on. Okay, sigma is an automorphism of Q adjoins square root of 2, adjoin cube root of 2, to Q adjoin square root of 2, to adjoin cube root of 2, right? So this is an automorphism. The point is, this automorphism is determined by its values on the generators, the algebraic generators, square root of 2 and square root of 3. So another way we often write automorphisms is by writing sigma dot dot and then a braces sign and then the action on the generators. So square root of 2 can be sent to something and square root of 3 can be sent to something. But okay, I'm going to write sigma of square root of 2 and sigma of square root of 3. So any automorphism is determined by these two choices. But how many choices do you have? This guy has 2 choices. It could either be square root of 2 or minus square root of 2, because the roots of the minimal polynomial of square root of 2 have to be permuted. So you have to take square root of 2 to another root of that's to a conjugate of square root of 2, either square root of 2 or minus square root of 2. And then this guy has to be in square root of 3 minus square root of 3. Oh gosh, I actually said something wrong over here. I said that, I just noticed that I said Galois group of cube root of 2 adjoin omega over, hold on, sorry. Galois group of Q adjoin cube root of 2 over omega over Q. I verbally said that this was Z cross 3Z, but that's wrong. it should be S3. So the symmetric group on 3 letters, right? The Galois group, but yeah, like I'm just correcting myself. Let's get back to this explanation. Right. Okay, so square root of 2 can be sent to sigma of square root of 2. Right. Notice here that q adjoin cube root of 2 adjoin omega over q. The degree of this extension is actually 6, which is the order of the symmetric group. 6. Okay. Yeah, whatever. That's that example. But in this example, we're looking at q adjoin square root of 2 adjoin cube root of 3. No, square root of 2 adjoin square root of 3. And we said that any automorphism of this field is determined by where it sends the generators, but you have finitely options for where it sends the generators. Here you have 2 options and 2 options. So actually, just from this computation alone, we see that the order of the Galois group the number of possible automorphisms is less than or equal to 4, right? But since this is a Galois extension, all 4 of those possibilities are actual automorphisms. So if I send square root of 2 to minus square root of 2 and square root of 3 to square root of 3, like if I make a certain choice, if I choose this and this, then that's a valid automorphism because the number of possibilities requires us to have that be a valid automorphism. So it's true that an automorphism is determined by its action on the roots, but sometimes you can't, like sometimes you'll have possible ways to map the root, the generators, which are not valid automorphisms. But in this case, all of these possibilities are valid automorphisms because we have 4 possibilities and we have to have 4 automorphisms because the degree of this extension is 4 and it's a Galois extension. So there has to be 4 automorphisms. So each of these choices gives us a valid automorphism. And now we know what the structure of the Galois group is. We have one automorphism, sigma, let's say, sigma, which sends, well, obviously we have the identity. That's always an automorphism. That one looks like whatever. I'm too lazy to change colors. So like this choice gives us the identity. This choice gives us square root of 2 gets sent to square root of 2, and square root of 3 gets sent to minus square root of 3. Sigma, let's say, is this choice. And then if you notice, if you compose sigma with tau, you're going to get the final choice. Square root of 2, square root of 3 gets sent to minus square root of 2. And then you apply, well, first you apply tau, which sends square root of 3 to minus square root of 3. And then you apply sigma, which sends square root of 2 to minus square root of 2, while fixing, yeah, okay, yeah, whatever. So you have this thing. And so the Galois group, let's write it as G, is generated by sigma and tau. But, right, so all of the automorphisms are generated by sigma and tau, but you have several relations. You have sigma squared equals tau squared equals the identity, and you have sigma tau equals tau sigma. And this is a presentation for the Klein 4 group, right? So Z cross 2Z times Z cross 2Z, or direct sum, whatever. So this is an abelian Galois group, and it's not the symmetric group. So this is not equal to S4. Even though this polynomial has 4 roots, all of the permutations of these 4 roots are not valid permutations, because you can't send square root of 2 to square root of 3. Even though both of those are roots of the same polynomial, they're not roots of the minimal polynomial of square root of 2. So from that perspective, you don't get that. Yeah. So this is an example of a Galois group which is not a splitting field, which is not a symmetric group. It's the Klein-Ford group. So the Galois group is 1 sigma tau, which is a Klein-Ford group. And then the main theorem of Galois theory is somehow relating subgroups of the Galois group to fixed fields. Remember, we talked about this correspondence, this inclusion reversing correspondence between subgroups of the automorphism group and fixed fields of the extension, inside of the extension. And when you have a Galois extension, this correspondence is a true correspondence. It's a bijection, one-to-one inclusion reversing and all that. So in this case, let's see how it plays out. You have, by the way, that's called the fundamental theorem of Galois theory, and we have to prove this, which we'll do in the next section or chapter. No, section. But let's see what it looks like in this case. So the subgroup that's just the identity, it's fixed field. First of all, what are the subgroups of the Klein-Ford group? There are, okay, I need to make this highlighter. There are these many subgroups, and there are only 3 non-trivial subgroups. So first of all, there's the identity subgroup that's always there, and there's the full group that's always there. And then there's the group generated by sigma, there's the group generated by tau, and there's the group generated by sigma tau. So these are all isomorphic to Z cross 2Z. And if you look at their fixed fields, these are all quadratic extensions, degree 2 extensions. So somehow that's the degrees of the extensions are related to the orders of these subgroups. And you have this correspondence. We can actually see in this example straight away like where these fixed fields are coming from, because the automorphisms are so simple to look at. So let's try to see this. So the automorphisms that, okay, so the identity, this fixes everything. So the fixed field is everything, always. Let's look at the fixed field of the whole group. Well, sigma changes square root of 2. So square root of 2 is not in the fixed field of the whole group. Tau changes square root of 3. So square root of 3 is not in the fixed field of the whole group. So it doesn't have any of the algebraic generators of this guy. So it's just Q. So the fixed field of the whole group is just Q. And this is something in general. The fixed field of the whole group is always going to be yeah. So this is something I should make a note of. We'll see it later as an alternative definition of Galois extension. So the fixed field of the whole group is the base field when this is a Galois group. Notice in the case where you had the extension Q adjoin cube root of 2 over Q, this is not a Galois extension. And what is the fixed field here? The fixed field of the automorphism group, Q cube root of 2. Oh gosh. Q adjoin cube root of 2 over okay. Yeah. So the automorphism group, this automorphism group, this is just the identity. So the fixed field is actually the whole extension, Q adjoint cube root of 2. So this is how bad this thing is from being a Galois group. Because I said this verbally, I didn't prove this yet, that you have a Galois group when the fixed field of the automorphism group is just the base field. So you have enough automorphisms that ensure that nothing is being fixed other than the base field when you look at it from the whole point of view. But in this case, the only automorphism is the identity automorphism. So the fixed field is the whole group. So it's like the opposite of a Galois group, because the base field is not the fixed field is not the base field of this automorphism group. It's the whole field. And that's how bad it is from being a Galois group. Okay, so we notice that the fixed field of the whole group is the base field, Q. But what about the fixed fields of these intermediate subgroups? So these this order 2 subgroups, you have 3 of them in Z2 cross Z2. And it turns out that you have exactly 3 quadratic sub-extensions of Q adjoin square root of 2 square root of 3. And these are Q adjoin square root of 3, Q adjoin square root of 2, and Q adjoin square root of 6. You can see how this is the fixed field of this guy, because what did I say sigma was? Sigma was the one that changes square root of 2 and fixes square root of 3. So square root of 3 is actually in the fixed field. So this shows that Q adjoint square root of 3 is in the fixed field of 1 and sigma. But why is it all of everything that's fixed? Because if you adjoin anything else that's outside of this, you'll get the whole field. But this does not fix the whole field. It in particular does not fix square root of 2. So that's why this is actually the fixed field of this group. And likewise, this is the fixed field of this group. And why is this the fixed field of this group? Because first you're altering, well, just look at what it does to square root of 6. Square root of 6 is the product of square root of 2 and square root of 3. So it sends square root of 6 the product of the images of square root of 2 and the image of square root of 3, which is negative square root of 2 times negative square root of 3, which is square root of 6. So this automorphism fixes square root of 6. So we're in the fixed field, and just the same argument shows that this is actually the fixed field of this guy. So in this specific biquadratic extension case, we see that the fundamental theorem of Galois theory is true, which is telling us we have an inclusion reversing bijective correspondence between the subgroups of the Galois group and the fixed fields corresponding to those things. Okay, I think we're out of time, but there are a bunch of more examples in this section. So really important to read these examples and understand them. Did you say earlier that even if you map roots to roots of the same irreducible factor, you don't always get a valid automorphism? I mean, if you do always get a valid automorphism, that would mean that the Galois group of any irreducible polynomial would be the symmetric group. Wait, no, it would not. No. So yeah, you can always map any particular root of an irreducible polynomial. No, not irreducible. I mean, any particular root of a minimal polynomial to any other root of the same minimal polynomial. So if you have an algebraic element, then you can have an automorphism which takes it to any other conjugate. Right? That's always possible. No. So there's a distinction between, so this is a good question. Let me make some space. Okay, let me it's spaced in the wrong place. So there's a distinction between sending a particular root to any other particular root and permutations of the roots. So in this case, we're saying that the Galois group is transitive, meaning you can take any root alpha to any other conjugate beta, right? If you have the minimum, oh man, come on. So if you have alpha and then you have the minimal polynomial of alpha, then you can send alpha to any other root of the minimal polynomial, beta. But if you have the collection of roots of this minimal polynomial, say alpha 1, alpha 2, alpha 3, dot, 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 alpha n, this statement up here, you can send alpha to anything else over here. That's not the same thing as saying you can have any permutation of this set, right? In one case, you get the existence of n different automorphisms. You get alpha gets sent to alpha 2, alpha gets sent to alpha 3. And these are all distinct automorphisms because you're sending alpha to different things. But that's only n distinct automorphisms. That's not n factorial automorphisms. Because sometimes when you take alpha 1 to alpha cubed, you're taking no, when you're taking alpha 1 to alpha 3, that's forcing alpha 2 to go somewhere else. But what it means to be a general permutation of the set means you can choose where alpha 1 goes and you can choose where alpha 2 goes, right? Yeah. So there are n factorial permutations, but sometimes that's more than the number of automorphisms that you can choose. Okay, good question. I'm gonna finish. So that's it for today's lesson, unless there are more questions. Okay, yeah, you're welcome. And yeah.